As a global company, we hear people say Viavi in a lot of creative ways.
Viavi.
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 Viavi. Viavi.
It could be because our name is comprised of a lot of vowels. Or if you were to turn it upside down, it's sometimes hard to figure out the right way up.
Lavia.
Lavia.
Lavia. Lavia.
We used to be JDSU, but today Viavi is recognized around the world as a leader in telecommunications and optical solutions with millions of installs. We may have a funny name, but our award-winning test solutions are no joke. They're everywhere, helping our customers enable the next generation networks that connect the world. But wait, there's more. We're also a leader in optical technologies. At Viavi, no matter how you say our name, we hope you remember us as the company that you rely on for your telecommunications and optical technology needs.
Viavi.
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 Hi, this is Peter Damaris with Viavi Solutions.
And this is Dave Baker. Welcome to our live stream on Ethernet Basics. We're going to discuss Ethernet network components, including cabling, optical transceivers, and network elements such as layer 2 switches. We'll explain common network performance issues associated with each component. Throughout the session, we're going to show you live demonstrations of Viavi test equipment used to assess and troubleshoot network performance. We encourage questions throughout the session, so please use the chat to enter your questions, and Sean Harmon's going to be moderating the chat for us. Most of the demonstrations that we show today are available online in both video and written format. Short videos can be viewed at the Viavi product training channel, and quick cards and videos can both be viewed at viavisolutions.com. Quick card are short documents in PDF format that walk you through the testing processes. With that, I'll introduce Peter Damaris.
Hey, thanks, Dave. So as Dave mentioned, we want to keep this today's presentation kind of open and interactive. Not quite as open and interactive as last night's presidential debate, but somewhat open and interactive. So like you said, anytime you want, just feel free to type in comments, ask any questions, and Sean will either respond or pop the questions in, and Dave and I will be able to stop and respond to you. But we want to keep this kind of interactive. So to start, this first slide kind of sets the stage for today's presentation. It's protocol models and layers, and it's basically there are two models that provide kind of a big picture view of how the network operates, from the physical hardware down at layer 1, the physical layer, up to the end user applications. So your emails or your file transfers or stuff like that. So the first model is the OSI model. It started back in, they started working on it back in the late 70s, mid 70s, late 70s, and then it was actually released in about 1984. The final version was released. The OSI model, it's designed, or it's made up of 7 different layers. And when we say layers, that's how we kind of partition the network into these different aspects. After that, there's the TCP IP suite. This is kind of an updated version of the OSI model. It was just 4 layers, and they just actually updated it one more time, and now it's 5 layers. So you will notice that layers 1 through 4 are actually the same, and then they just combine layers 5, 6, and 7 into the application layer. So each layer in the OSI or the TCP IP suite has its own protocols. So what are protocols? Protocols are a set of rules, excuse me, that define how networking devices should work, and not only how they should work, but how they should work together. And that was kind of the purpose of putting together this whole OSI model TCP IP suite. It was to make sure that if you had an Apple computer and you were sitting in Boston, Massachusetts, that it would communicate with a Dell computer out in Singapore. So we have different protocols and then the different layers. In addition to that, each protocol has its what's called a PDU. And the PDU is it's called a protocol data unit. And each segment, it's a specific block of information that's transferred over the network. So in this case, layer 5, the application layer, is the PDU is data. As data gets passed from layer to layer, it becomes, they call it encapsulated. We won't get deep dive into this. Today's just an Ethernet basics, but it gets encapsulated, and we change that from data, it becomes a segment, goes to layer 3, the IP layer, or the networking layer. IP sources and destination addresses might get added, and it becomes a packet. From the packet, it goes to layer 2, becomes the data link layer, and now it's frames. So we may get the MAC address, the switch, the source and destination address get added to it. And then from the frame, it goes down to layer 1. Layer 1 is the physical layer. It's the cabling, or it could be wireless. We're not going to get into wireless today, but Could be cabling, wireless, and you'll see the different protocols there. There's Sonnet, Ethernet, T1, Wi-Fi, DOCSIS. And at that point, it's a bit. It's ones and zeros. And if we're dealing with a LAN, a local area network, then it's going to go out. It's going to be electrical pulses sent out. If it's going over a wireless network, it would be RF. It would be radio being transmitted out. So that's kind of an overview. For today's presentation, we're going to just focus on layers 1 and layer 2, the physical layer and the data link layer. Again, physical layer, all the cabling, all the connectivity. Some devices fall in that physical layer, but it's really how the device is connected to the next device. And then we'll also talk about that data link layer, excuse me, also. And that data link layer is where the physical the frames and stuff are sent between devices. So with that, we're going to get into Ethernet cabling. So we talked about it could be fiber, it could be copper. If it was wireless, we'd get into the radio, RF. So there are some common Ethernet physical layer standards. And by that, so the standard, you'll notice, it lists, we've got a list of the standards, we've got the name and then the description. So in the standard, you've got the speed, it's followed by base and followed by the media type. So just by looking at any one of those standards, if you've got the cheat sheet, you'll be able to tell exactly what the speeds are, what the signaling is, and then what the rates are and how it's being, what it's being sent over. So the first number, that represents the speed. If there's no suffix, for example, 1000 base T, if there's no suffix after that 1000, then it's megabits. Down below, you'll see 1000 G, 10 G base LR or 100 G base. G just stands for gigabit. Next section is just the signaling type. It's base, broad, or passband signaling. Next is the letter, and this is where you'll see for like twisted pair cabling up top, it's got a T. An S in the standard just signifies it's 850 nanometer. It's a short range, typically over multimode fiber. And then an L is long range, typically single mode. And then down at the bottom, you'll see an F, and that's just fiber of various wavelengths. So these are some of the standards and at the physical layer. And as we mentioned, you'll see the different types of twisted pair, multimode fiber, and single mode fiber. That's what we're going to kind of focus on the for the physical layer. Copper twisted pair. It can be shielded or unshielded. Down in the bottom, let me grab a pointer here, laser pointer. So down in the bottom here, we've got a UTP unshielded twisted pair cable. Just above it, we've got a shielded twisted pair cable, just an overall foil shield on there. There's two methods of terminating a cable in a network or in anywhere, just into an RJ45 if it's a patch cord. There's TIA 568A standard, and there's a TIA 568B standard. In Canada, most of the time you'll see 568A. Canada, and actually in the US government, a lot of the punch downs, as we call it, are 568A. So the pairing is as shown there. In the US commercial buildings, we typically use 568B. I'd say 95% of the time it's 568B. If you look, the only difference there is the green pair is 1 and 2, the orange pair is 3 and 6 in the 568A standard, and in 568B, it switches it, and the orange pair is 1 and 2, and the green pair is 3 and 6. The other thing with Ethernet cabling, a lot of times you'll hear the term category 5E, category 6, category 6A. What does that mean? It's basically the higher the category, so 5E to 6 to 6A, there's a different frequency range or bandwidth of the cable. In this case, 100 megahertz for Cat 5E, 250 megahertz for Cat 6, and 500 megahertz for category 6A. And then you'll see what the networking standard is that it supports. So 5E cables will support 1 gig. Cat 6 will support 1 gig, but to a higher frequency. And category 6A will support up to 10 gig. There's another standard out there that's was released about 2 years ago. It's category 8, and that's designed to support 40 gig over twisted pair cabling. So in copper cabling, when we're testing that, we typically use a cable certifier. A cable certifier is going to take these 13 tests, and it's going to test that cable, not only to make sure that the cable was manufactured and the quality of the cable is good and the quality of the connectors are good on the end, but it's also going to test the installation. So you could have perfectly good cable, perfectly good connectors, punched down, everything's good, and when it gets installed, all of a sudden we've got failures. These are the different standards for a TIA certification test. Again, there's 13 of them listed here. There's a couple other optional tests that you can do, but to certify a cable, these are the 13. The most common source of a failure would be near-end crosstalk. And that kind of plays into a lot of the others. So if it does fail near-end crosstalk, it's going to fail power sum near-end crosstalk or attenuation to crosstalk ratios and stuff like that. There are different, when I mentioned that a cable certifier actually tests the cable, but also the installation, there are certain guidelines to terminating and working with the different cables. You can't bend it more than 90-degree bends. You can't strip the jacket back more than a ½ inch when you're terminating it into a cable, and that's all due to those pairs. If you look at the pairs within a cable, if you took the jacket off a category 6 cable, the pairs are going to be twisted a lot tighter than if you took the jacket off and looked at the pairs on a category 5E cable. So, so what we're going to do now is do a quick little demonstration just on copper testing demonstration. Dave's going to use a T-Bird 5800, and when he's done, I'll show you cable certification quick test on the certifier, Viavi Certifier 40G. So over to you, Dave.
Thank you, Peter. Most Ethernet test sets will provide some basic copper cable testing features. For example, the T-Bird 5800 has a distance test that I've already run. It's shown that I have about 3 or 4 meters of cabling here, and it's open at the end. I'm not terminating in a switch currently. If I was 0 distance, that would indicate the cable wasn't terminated properly at the beginning. Or maybe if it failed at 2 or 3 meters, there's an open or a short in there somewhere, and that would be indicated in the fault type. I can also do a pair test, after which it'll identify my link speed, and I am bringing up a full 1 gig link, and I have continuity on all of the pairs to the switch. Now, this is useful just to make sure that my cable's okay and that I have continuity across my network, and I can, I have a decent cable, but it is by no means cable certification. A different class of equipment is required for full-blown cable certification, and Peter's going to show that to you now.
All right, so we mentioned earlier that that a cable certifier, and we do about 13 different tests on a cable. Just wanted to show you, this is the screenshot off of a Viavi Certifier 40G. This is our cable certification tool. In this case, we've run a test. I hit the start test button. In about 10 seconds, the test will complete. It'll show you if it passed or failed. This is the cable ID NPD-ECD-2. Shows the next cable we're going to test is NPD-ECD-3. If I want to zoom in on any of those particular tests, I can hit this magnifying glass at the bottom, and it'll bring up a more detailed listing of all the different tests. So that's kind of the copper cabling world cable certification using a Certifier 40G, and then also using the T-Bird 5800. So next we want to get into fiber optics. So before we do that, there is one thing I forgot to mention, and I'm going to go back here and just quickly show you, bring it up, because we want to keep this interactive. On the OSI model, to try to remember that, there's mnemonics that you can use. And so what we're going to ask you guys to do is kind of come up with your own, or tell us which mnemonics you use to remember these. So for example, to try to memorize the OSI model, someone may say from layer 1 up to layer 7, please do not throw sausage pizza away. And that's how people that are taking the CCNA exams and that will remember the OSI model. For the PDUs, even better one, reading it from the top down instead of DSPFB. Don't stop pouring free beer. Pretty easy to remember there. So as we're going through this, kind of shoot into the chat window, type in any mnemonics that you may have that may have helped you, or remember these. So with that, let me jump back up to my fiber optics. So we've gone through all the copper. Let me just show the fiber side of things. So before we talk about fiber optics and the types of cables and all that, the number one thing that we must talk about is inspect before you connect. If you're doing any Ethernet work, anything in a data center at all, the key to the whole thing is inspect before you connect. What I mean by that is the end faces on the fiber will get dirty. Very easy to dirty an end face on a fiber. So Viavi's come up with this, we call it IBYC, inspect before you connect process. Basically, inspect the fiber. Is it clean? If yes, then go ahead and connect. If it's not clean, then clean it and go ahead and inspect it again. About 90% of the time or higher, if you sit through some of the leading fiber optic manufacturers' presentations, one of them had it as high as 94% of fiber issues, networking issues, has to do with dirty end faces. The problem with that, you plug a dirty fiber into a piece of test equipment, you're going to contaminate that port. You plug it into a switch or connect it to another fiber, it's going to contaminate whatever it's being plugged into. That extra dirt on there is going to create loss. It's going to create air gaps and just a lot of issues. So always inspect the fibers before you connect them anytime you're working with them. There's two types of fiber optic cable, multimode and single mode. You'll see here on the top, these are the different core diameters. You may have heard 62.5 micron core, 50 micron core, or in single mode, a 9 micron core. 62.5 is OM1. OM stands for optical multimode. It's designed for LED type light sources. 50 micron is designed primarily for laser light sources. So a VCSEL laser, for instance. Again, there's OM1, OM2, 3, 4, and 5. The higher the number on there, the better distances, the higher bandwidths can be achieved with the fiber. And then on single mode, you'll notice it's just a small core diameter. So what do we mean by multimode? Multimode, it just means we're sending, exactly as it says, multi-modes of light through the fiber. It's used for short distances, short distance applications. From that chart that I showed earlier, you'll see that a lot of the multimode fibers are all short range. It's got a larger core, as we showed, different paths to transmit the light, different modes to transmit the light. It's sensitive to modal dispersion or a delay between the different modes. And it's primarily used, again, because it's short distances in LANs, local area networks, in building applications. You could have fiber to a desktop in an office environment, and in data centers. Again, data centers are short run, so a lot of times you'll see multimode fiber installed there. Single mode, on the other hand, is just a single mode of light going through the fiber. It's used for long distance applications, much smaller core, single path or mode to transmit the light. It's used in very high speed transmissions. And then the applications for that are telecom, CATV, or DCI, data center interconnects. And it'll support CWDM and DWDM, where we're using different waves on the fiber, without getting deep into that. So a single fiber versus multi-fiber. Some of those networking, the protocols that I mentioned, down at the bottom, they had different waves. Different number of lanes. This on the left-hand side is an LC connector. On the right-hand side is an MPO connector, multi-fiber push-on connector. This is becoming more and more popular in data centers and in Ethernet applications. It's because of port density. Everybody's trying to do more with less. So this fiber on the left, and this is actually the end face, a look at the top of an SFP. You'll see there's 2 ports on there, 2 LC ports. So this will hold 2 fibers. The same size SFP on this side is an MPO. This is going to support 12 fibers. So MPOs can go up to 12, 24, can go a lot higher than that. The most typical ones we see are 8, 12, maybe 16, and then 24. One thing to note when looking at the 2 different types of fiber is one has a white ceramic ferrule, so the outside of this is nice and clean when you look at it in an inspection scope. And on the right-hand side, this has a polymer ferrule. This is actually an inspection image of an MPO using our Sidewinder, and Dave's going to do a demo on that in just a second. So common types of MPOs, MPO or MTP. MTP is a registered trademark of US Connect, which is part of Corning, owned by Corning. So anywhere you see MTP, an MPO cable can be used. So, all right, what are some of the common issues with fiber optic cables? Number 1, as I mentioned earlier, fiber end face contamination. The end of that fiber gets dirty. You're going to have loss. You're going to have a lot of issues on the network. The solution is fiber optic cleaners, those one-click cleaners, or use inspection microscopes. So first use the inspection microscope. If it's dirty, then use the cleaners and clean it. For MPOs, they always suggest a wet to dry. If you can't get it clean that first time, use a wet to dry clean on it. Also issues with fiber is misrouting. I'm going to show you an example of a visual fault locator, a VFL. Some people call it a VFI, a visual fault indicator. Also, high signal loss. Some of the reasons for high loss is excessive length, bending, bad splices, bad connectors. And we're going to show 2 different examples of how you can measure that loss on a fiber. We're going to use an optical loss test set, and then Dave's going to use an OTDR to show any breaks and cracks and the events along the fiber. So with that, we're going to do a couple of demos on inspection tools, optical loss test sets, and an OTDR. So over to you, Dave.
Thank you, Peter. Now I have a fiber inspection microscope here for MPO connectors. We look at the base of it. I have an MPO connected. I've already tested this MPO cable, and you'll notice it failed. There are several fibers in this MPO that are fine, but there are also several fibers that, that failed. The summary at the bottom here. So if I were to connect this up to my network, I would risk damaging the equipment. I would also, in best case, have a reduced signal level and perhaps not be able to pick up the signal in order to, for an SFP or optical equipment to recognize it, and I'd end up with a high error rate on the network. I also have a regular Simplex microscope connected up here. This is a microscope just to look at single fibers, our fiber check probe. And I'll do a live demonstration of that. I have a cartridge here with some fibers in it, some bulkhead connectors with fibers in the back, and I can simply insert this into the cartridge and run a test to assess that. That's a dirty fiber. Yeah, this one's a little bit cleaner. Testing's real simple, just one pull of the trigger, and it will focus the fiber. Pull again and hold, and it'll test and give me a pass-fail analysis. So again, this is an invaluable tool in verifying whether your connection points are clean and whether you are ready to go ahead and connect a cable to it or not. Dirty fibers, as Peter highlighted, are one of the key problems that you're going to have in your Ethernet network connections if you don't clean properly. So on to you, Peter.
All right, so the next one I want to show is just the VFL. I talked about a VFL or a VFI, Visual Fault Locator. This one, I apologize, is an older one that I've got here. It still has the JDSU logo on it. JDSU is now Viavi Solutions, for those of you that didn't know. Basically, I'm going to plug, I've got here an SC, just a short little jumper that I'm going to use for demo purposes today. It's got an SC UPC connector on the end of it. I'm going to plug that into the top of this VFL. And when I do, I turn that on. Basically, all a VFL is an LED source, or I mean a laser source. So it's going to send a laser of light down the fiber. And if you notice, the end of that fiber is lit up. What that does, you plug into one end of a fiber and you have no idea where that is at the other end. Let's say your labeling wasn't done right, or it's mislabeled, and you have no idea where that fiber is being run. With a VFL, you can plug it in, turn it on, and you can see exactly where that fiber is. The port on that, where that fiber is terminated, will be flashing red. You can turn it from a solid. I can click on this. Usually people like it just always on, the solid red, because in a data network and a data center, there's a lot of the flashing red lights in that. The other thing you can do with this, with a VFL, is when it's shined down the fiber, you can find, and I'm not sure how well this is going to come up on the screen there, but you can see there, and I'll make it toggle on and off. You can see there that if I put a bend, it's going to start glowing. So any imperfections in that fiber are going to come through. Now, it's not an electronic thing. You've got to shine a light on it, and you'd have to physically walk down the fiber to see where the error or where the fault is. But it's an inexpensive, quick tool, excellent for doing exactly what I said, to locate the other end of the fiber, and then, as we said, to walk down the fiber and find where the fault might be. The other tool is an optical loss test set. So this one here that I'm demoing here, this is an actual screenshot of my MPO-LX. This is an MPO optical loss test set. If I hit the start test button on here, it's going to ask me if I want to save the result that I just had on there. I'm going to say no, and it's going to run a test. It starts the test. This is going to give us an optical loss test set, is going to give you length, loss, and polarity. These are designed to give you an overall loss of the fiber run that you're testing. It's a dual-ended test, so you'll see here, I've got one unit on the near end, at the local end. I've got one unit at the far end, at the remote end, and we're running this test. So the results you can see on the screen, like I mentioned, length, loss, and polarity. My length is 7.2 feet. I've just got a short little jumper between this just for demo purposes. My loss in this case is 0.68 at 1550. It's 0.84. And then my polarity, if I click on that, it'll show me the actual polarity of the fiber that we're looking at. If I click on 1310, it's going to give me all my loss values on that fiber, and click on 1550. So optical loss test set, what this doesn't do is doesn't give you the distance to fault on any of the events. It's giving you an overall loss from point A, from the local device to the remote device, of that fiber. If this test had failed, then we would take out an OTDR and run an OTDR trace to find the events and to find where the distance to that fault is. So with that, I'm going to switch it back over to Dave, and he's going to show you an OTDR demonstration.
Yep, so this is an OTDR. This is our T-Bird 2000. It has a connector on the top with a SC under it, with which I could connect up to a fiber under test. So not only will this measure the length and the loss on the fiber, but it measures the length and loss for individual events. So every connector, every splice, if there's a bend on the fiber, it's going to identify all of them. So let me demonstrate that to you here. Our OTDRs operate in a couple different modes. There's an expert mode for advanced users, but the simplest we call smart test, and that's what I've launched here. There's only 4 settings, so a novice user can quickly pick up our OTDR and get value out of it. You have to select the lasers you want to run the test with. We usually recommend you using 2 different wavelengths. That enables bend detection, but in the interest of time, I'm just going to do a single wavelength. You specify the distance unit. I'm going to show my distance in meters. You specify how long the cable is that connects your OTDR to the line under test. I'm actually using a different OTDR, but it has a 20-meter cable on it. And finally, you can specify user alarms if you wish to, but I'm just going to go with the defaults. So I simply tap the Smart Start Test button, and in a few seconds here, I'm going to have the results for this fiber trace. I actually have 2 10-kilometer reels of fiber that are interconnected with a few jumpers. So that's what I expect to see in the results here. Just a few seconds away. And there we are. This passed. The total length of the fiber and loss is shown here, as we could get off of a loss test set, but also I see all the individual events. I see the end of my launch reel. I see the different connectors, and things highlighted in green are good. If there was anything that had excessive loss or problems, it would be highlighted in red, and I'd see alarms at the bottom of my screen. So OTDRs let you see all the individual events.
All right, so we do have a question that came in. Is there a different a distance limitation on the MPOLX test set, and can it make it through optical splits? So if I just go back and share that screen, I think I shut it off, but we're going to go back to device, and there it is. So you'll see on here the standard that I'm testing to. In this case, it was 1,700 feet. It'll go up to, I believe the limit's 3,000 feet. I'd have to confirm that, but there is obviously the amount of signal strength that we're putting out. There is a limit on there, and it's in our data sheet. I don't know it off the top of my head. I apologize. We can definitely get that to you. And then the other question on there was, can it make it through an optical splitter? So no, this isn't designed for a PON type environment. This is just a point-to-point without a splitter in the middle of it, where we're doing from the local unit to the remote unit. So it will not test through a splitter in that case. All right, so if there's any other questions, I'm not seeing any of those mnemonics coming in yet. And one thing I didn't mention is please keep those clean, because there are a lot of them out there. So let me close this. And in just a second, so Dave's going to get into Ethernet network equipment. So we've talked about the physical layer. We said we're going to focus on layers 1 and 2. 1 is the physical layer. We talked about different types of copper, the protocols, different types of fiber, and then how to test those. Now we're going to get into the Ethernet network equipment and the tools, the equipment that's involved. So go ahead, Dave, over to you.
Thank you, Peter. We have another question? Okay. I have a question about when I connect to MTS or T-Bird 5800s with layer 2 test, can configure ATP or BERT. We'll actually get into that in the presentation. So I'm going to defer this question, and we'll talk about Acturna test packets, ATPs versus BERT patterns. So yeah, let's hold on to that for a minute. Okay, I have here a diagram of maybe a typical enterprise network. Provider networks, have a lot of the same components in it, but basically, so far we've talked about cabling that are going to interconnect two devices. So maybe a PC to a switch, or a phone to a switch, or a switch to a router. The cabling has to be good. Now, the devices that interconnect all the equipment on the network are switches at the Ethernet layer, and then routers at the network layer at layer 3. Again, today's focus is on Ethernet, so I do want to talk a little bit about how switches behave and and things that can go wrong and things that you can do to test and verify that your switches are working properly in addition to the cabling. Now, switches, as well as most of the end equipment, like your PCs and phones, will have potentially optical ports as well as copper ports. Copper ports are typically fixed connectors. Optical ports are typically just cages, just a hole that you can insert a module into in order to do testing. This is see the size. This is the size of some pluggable optics. So here's a couple examples of things you might plug into a switch port in order for it to support optics. The pluggable optics are called SFPs and QSFPs. SFPs are the smaller form factor. QSFPs are a little bit larger form factor, and they support higher rates. So at the low end, a regular SFP would only support 1 gigabit Ethernet. but SFP pluses can go to 10 gig, and there's even SFP 28s and 56s for 25 and 50 gig Ethernet. QSFPs today typically start at 40 gig, but QSFP DDs support the latest Ethernet rate. We're starting to see 400 gigabit, but they're plugged into switches in order to provide the optical connection. Now, QSFPs and SFPs differ in their form factors, but they can also differ in the wavelengths they support, their reach, and the protocols that they support. Multimode optics are normally 850 nanometer, and they're limited to pretty short reach, maybe 200 meters or so. Single mode optics predominantly are 1310 and give you a reach of 20 kilometers or so. Some are a little bit less, some are a little bit more, but with single mode, you can go over longer distances, and that's why they're typically used on wide area networks or longer distance connections. 1550 nanometer optics are a little bit more expensive, but they support extended reach. They may be spec'd at 80 kilometers, plus or minus. So it's important to select optics that have the correct reach for your application. Now, optics can be designed to support different protocols as well. Today's discussion is on Ethernet. So if you're using Ethernet to test anything that we discussed today or to support anything we're discussing today, you want Ethernet optics. But optics could be designed for fiber channel or OTN or SONET or CIPRI or any fiber-based protocol. Some optics are multi-protocol and can do a range of them, but some are specific to one protocol and may not be able to support Ethernet. The bottom line is you got to make sure you have the right optic to support the application and that has sufficient range to be able to get to the far end of the network. Otherwise, you're going to have issues. There's simple tests that you can run with most test equipment to verify that the optic is working properly for the rate that and application that you intend to use it for. And I'll show you that shortly. Most optics have an LC or an MPO connector on them, which you connect up to a fiber. Again, you want to ensure the fiber's clean before making the connection, but then you could use any fiber variable length patch cables to connect up to your line under test. Some SFPs have fibers permanently attached to them, or copper permanently attached to them for that matter. They're called AOC cables when they're optical, and DAC cables when they're copper. So these present special challenges when you're testing because you can't measure loss across the fiber. You don't have access to the fiber for testing. So in order to test these, you need to test SFP cage to SFP cage, and test equipment can be used for that as well, as long as it has 2 ports on it. We're going to demonstrate that to you shortly too. Again, these optics are typically inserted into a switch for Ethernet connections, or router, or perhaps a server. But the ports on the switch that support these are commonly called trunk ports, and they're the higher speed ports that connect up to the remainder of the network, at least for edge switches like this to support users on phones and routers. So a given switch might vary in the number of copper ports it have and the number of optical ports and the speeds of them. So this is a work group switch pictured here that has a lot of copper ports on it. So several PCs and phones in a floor or a section of a building might be connected up to this, being installed in a wiring closet somewhere. Whereas the uplinks would be connected up to the core network, to the internet or the intranet in order to provide connectivity to the remainder of the network. Switches can be managed or unmanaged. Now for enterprise and telecom applications, you typically need managed switches that provide some additional capabilities beyond unmanaged ones, which are pretty much plug and play. In your home network, you may use an unmanaged switch, but you want to be able to set parameters on enterprise networks and service provider networks. Management is important. Once a device connects up to a switch, the switch and device attempt to establish an Ethernet link between them. They try to bring up the data link, try to bring up the physical layer, and then bring up the data link. Now, in order to bring up the physical layer connection, both sides have to be operating at the same data rate, and a few other things need to be set common to both pieces of equipment. For copper connections, there's a negotiation that typically goes on between the two pieces of equipment where a common speed and duplex is selected. It's called auto negotiation. So as soon as that link comes up and current is seen on that cable, both devices are going to advertise what their capabilities are. In this example, T-Bird was set to advertise it could do 10 meg and 100 meg, although it supports a gig and 10 gig too, but you have control over that. The switch is advertising it can go all the way up to 1 gig. The two devices will choose the highest common denominator, which in this example would be 100 meg, and establish a full duplex link at that rate. Now, you can override this in equipment. You can turn off auto negotiation in equipment and specify that a port is always supposed to be 100 meg full duplex, for instance. If that's done, it has to be done on both pieces of equipment and set exactly the same on both, or else either the link won't establish, or worse yet, it might establish, but be half duplex or have some other erroneous settings that will cause it to error. There's no way to get a common denominator when you're not getting messaging from the other device. So commonly, equipment will default to half duplex, and you can't transmit and receive at the same time. So whenever traffic is being transmitted, it misses the received traffic, and vice versa. So that's something you want to avoid, and that is something you can test for and verify with test equipment if you don't know what the setting is on the port that you're connecting to. Optical's a little simpler. Typically, when light is seen on both sides, there's still some auto negotiation that takes place, but normally, it's on both, and the links will come up as long as light's seen on both sides. Once the link is established, then the data link can come up. Data link allows frames to be sent, as Peter described earlier. This is layer 2. The messages that are sent back and forth between the equipment include overhead for the switches to be able to know where to forward traffic to, and overhead for error detection to take place as well. So the beginning of every message that's sent on Ethernet has two addresses called MAC addresses. There's a destination MAC and a source MAC. The source MAC is a unique identifier for the device that is sending this message. So my PC has a MAC address on its network interface card that uniquely identifies my PC when I connect it up to the switch or the router in my network. When I want to send information to the switch or the router, the messages that come from my PC have that device's destination MAC in it. So these are important addresses that allow the switches to know where to forward traffic to. Frames have a variable length data field. It can be anywhere from 46 to 10,000 bytes. These carry the payload for what we need to test, or carry the payload for the application that is going to go across the network. So it's going to be an IP header for layer 3. It's going to have overhead for the different protocols, but eventually it's going to carry the web page that you're transferring, or the file contents that you're transferring with FTP, or the voice that you're transmitting with real-time protocols. So all that's going to be in the data field. When you're testing equipment with a device such as the T-Bird, it's a test packet. We call them ATPs, Acterna test packets, Acterna being a prior company name, which we trademarked these packets under. But it could also be a BERT pattern, be a bit error rate pattern, and we'll look at that when we move on to the demonstrations. I think there was a question that was posed in that regard. Then finally, at the end of the frame, there's an error checking mechanism called a frame check sequence. This allows errors to be detected when frames are received. A value is appended to every frame when it's transmitted, and that value is calculated based on all the bits in the prior fields in the frame. When the receiving equipment gets the frame, it's going to try to calculate a frame check sequence based on that same sequence of bits, and it'll get the same value as long as nothing's changed in transmission. But if there were errors in transmission, it'll be a bad FCS. The device will detect that and we'll be able to react appropriately. So the layer 2 basically provides means of addressing and a means of error detection and a means of transporting data. That's what the data link layer is responsible for in Ethernet. So switches, again, one of the main devices that need, as well as the end equipment, but they're an important piece of equipment that needs to look at these frames and process them. Now, one thing switches do is error isolation. That frame check sequence allows switches to isolate errors to a given port. Whether it's a managed switch or an unmanaged switch, it's going to do this. Whenever traffic is received in error, it's basically just discarded. It's not going to be forwarded on to the trunk ports or forwarded on to any other user ports and cause issues with them or congest their links with garbage. Another function that Ethernet switches perform is address learning. Now, prior to switches, device called hubs were used in networks, and they were basically multi-port routers. Traffic would come in on a port, and it would go out every other port, whether it needed to go or not. But modern switches have intelligence built into them to only forward traffic where it needs to go. They maintain a table identifying the MAC address, the source address of every device on every port. So those devices could be phones, they could be PCs, they could be other switches with multiple devices on them. But it'll be a table with the MAC address of all the devices as it learns them. And using that information, it only has to forward traffic to the port that it needs to go on. So if this PC wants to send a print job to a network printer, the traffic is going to have the MAC address of the printer, and it's only going to be forwarded out that one port. It doesn't affect the bandwidth for other users. It doesn't affect the bandwidth on the trunk port either. Switches can also organize the different ports into VLANs or virtual LANs. So managed switches do that in order to be able to prioritize traffic. Now, without VLANs, without prioritization, all traffic's considered equal. So if a user is gaming on a PC, another user is talking on an IP phone, a TV is receiving streamed video to play back some Netflix, another user is browsing web pages. Yeah, it's all equal. Voice is the most sensitive to frame loss and delay because it can't be retransmitted. So with a managed switch, all the IP phones could be put on a different VLAN, say VLAN number 2, and could be assigned a higher priority so that that traffic would be sent across the links first. And if traffic had to be dropped because of congestion, the voice would be given prioritization. So VLANs allow that to happen in enterprise networks. On service provider networks, VLANs are commonly used to differentiate customers or to differentiate different sites for a customer. And separate MAC address tables are maintained for each VLAN. So yeah, one VLAN is isolated from the other. VLANs require an extra field to be inserted into Ethernet frames. So after the MAC addresses, there's a VLAN tag, an identifier to let the equipment know it's a VLAN tag, and then the priority for the traffic on that VLAN, as well as the ID for the VLAN. In our example, 1 or 2 would be stored. And again, voice has higher priority, data has lower priority in general. Another things that switches do is buffer traffic. So multiple devices could be transmitting traffic into the VLAN into a switch concurrently, and maybe it's all destined out the trunk port. If these were all 1 gig ports and I was getting a full gig of traffic from one device, hey, that high priority traffic is going to get through. The lower priority traffic would have to be buffered up, and eventually the buffer fills up. There's only limited amount of buffer memory on the switches. So if traffic continues to come in, the high priority may continue to go through, but low priority traffic gets in the buffer and eventually needs to be discarded. Once traffic subsides Any information that accumulated in the buffer then will be flushed out and forwarded out. So this has a few things that impact your network performance. For starters, yeah, any traffic that's discarded will have to be retransmitted by higher layer protocols. And any traffic that's buffered has longer delays, so that can aggravate your response times as well. So we've identified several things that potentially could go wrong in switches and in the data link connections. You could have bad cables, you could have bad port or optics or incorrect optics. Misrouted cabling is commonly a problem too. We saw a relatively small switch with maybe 30 some ports on it. And even if you do have proper cable management processes, it's possible to mislabel a cable, plug it into the wrong port. If the port's on the wrong VLAN, you don't have any connectivity. Managed switches require some configuration in order to work. The VLANs have to be mapped properly. Auto negotiation may need to be set if people want to disable that. It could potentially cause issues. Ports could be just shut down and not enabled. And then buffering can cause issues with delay and congestion and dropped frames. I want to give some examples of equipment that we can use to and tests we can run to evaluate each of these issues. So on to you, Peter, for the AOC DAC cable test.
All right. So thanks, Dave. So what I've got set up here is I've got a T-Bird 5800. We mentioned this is an AOC DAC. I know there was a picture in one of Dave's slides there. It's an AOC DAC cable. It's basically it can be AOC is active optical cable, DAC is direct attached copper cable with an SFP built right into it. So these come directly from the manufacturer. You got to specify what length you want and what optics you want on the ends. Very pricey, very expensive cables. In the T-Bird 5800, we've added a test suite that automates the process of actually testing these. We've been on site. I know I've been on site, and we see guys have buckets of these things that they just pull out of the network and they throw out because they think it's a bad AOC or DAC cable. This allows you to actually test it. Two ways of testing. You can either, if you've got a 5800 that's got dual port, you can loop the cable back onto itself. That's good if I'm just testing, like I said, a cable such as this, just a short patch cable. If you're testing a longer cable, it's across the data center, then you would use two devices, one on each end, because obviously you can't loop it back to itself. So I'm going to do one. I've got an AOC DAC cable plugged into my 5800, and I'm going to loop it back. I've turned on the second port, so we're good to go. I've set my test duration to 30 seconds. This is the header. So when I'm done with this test, I want to show you how we can actually generate test reports. So we've got the customer name, technician ID, test location, work order number, and all the information if you wanted to generate the reports. This is also good where we've seen this used is for cable assembly houses. The people that actually manufacture these will use a 5800, do some testing on it, and then generate a test report where they can take that PDF, put it with the actual AOC or DAC cable, and package it up. So just show you, I'm going to start this test. Again, it's a pretty automated test. Just hit the start test button. I've got it set for 30 seconds. While that's running, this is my SFP on the end. I can click on that. It's going to give me all of the information about the SFP. In this case, the vendor name, part number, serial number. On the right-hand side here, we've got the bit rate. So you may notice this is it's a 40 gig, 40G base CR4 QSFP that I've got that I'm testing. It's a 40 gig cable, but the nominal bit rate's only 10. That's because it's a 4 lane. So we're taking 4 lanes at 10 gig to get that 40 gig. So we ran the test. The test actually passed. I can go in. It's done a bit error rate test. It's checked the signal. Everything's good. Everything's passed. I can now, you'll see at the top here, it shows that it passed. I can now go over, create a report, click on create report. All of that header information is going to be transferred over. If I fit this to the width, and you'll see on here that, let me change this here to fit to height. You'll see on here all of the information. You can't really see that, but it's give you a good idea of what the report looks like. So it's got all the information that I just talked about, all the information on that QSFP screen that popped up, manufacturer, part number, serial number, specific to that particular cable. So that's a AOC DAC cable test. So it'll prevent from throwing out good cables that are expensive cables when there's really nothing wrong with them. So I'm going to switch over to Dave now. He's going to do some other demos.
Yep, thank you. I'm going to show you the optic self-test. Now, an individual SFP can be tested in the same manner, but in this case, it's just a single optic. Now, to loop the optic back to itself, you can use just a regular LC to LC patch cable or a loopback plug such as this. This would be a loopback plug for an LC. This is a special loopback plug for an MPO that could be plugged into a MPO SFP to provide a loopback. I've done that, and I've already actually tested this QSFP, and it came back and passed. But kind of the same thing. It's going to verify the bit error rate. It's going to verify skew. It's going to verify you have an acceptable signal level and let you know if your optics are good or bad. If you have bad optics, obviously your Ethernet links aren't going to work, and this allows you to isolate down to that versus a different network issue. Another test that I want to show you is for verifying connectivity. So when installing equipment at a given location, it's important thing is to know that you have connectivity to your local switch. And there's two tools that are available in our toolkit that'll let you do that. One called a link connectivity test, the other protocol analysis. I'll show you link connectivity first. Link connectivity just lets me toggle the port on and off. I can tell it to do it every 3 seconds or whatever, however often I want to, and say how many times I want to do it. Once I start this, I have to actually walk to the switch. I can't show you the switch now, but once I do it, it would blink on and off the port that this cable was connected to. Now, if I have records that say that this cable is supposed to be connected to the 5th port, but the 4th port is the one that's blinking on and off every 3 seconds, I know my cables are misrouted. So that's something that would need to be corrected if I was turning that up, because maybe I was plugged into a port designed for IP phones when I'm a data device or vice versa. Now, again, that's a real useful tool, but it does require you to be in front of the switch to get that information. The protocol analysis tool lets you see that information without even being at the switch. It looks for messages that are typically broadcast by switches. There's a protocol called CDP on Cisco switches, which I happen to have in my lab. There's another one called LLDP that this will work with as well that many other switch manufacturers do. But every minute or so, they'll broadcast out information indicating what port this cable's connected to. So my links come up, and this is telling me I'm on the 4th port on this switch, and it even tells me what the VLAN is and the IP address for that switch port. So I get additional information here. But this can be real useful in verifying that your cables are routed properly. Because again, plugging into the wrong port or the wrong switch, for that matter, may definitely cause issues in your connectivity. So with that, we'll move on to network performance testing. Peter, back to you.
All right. So network performance testing. So we've gone through the physical layer. We've talked about all the different equipment and configurations and different things there. Now let's see what tests we can actually run on that physical layer and on that equipment to guarantee that our network is going to be working as expected. So some of the things that we use, key performance indicators. So this is a list of the most common, the 4 most common key performance, KPIs, key performance indicators. Throughput, and you've heard Dave mention a couple of these in his presentation earlier in some of the slides. So throughput, the amount of error-free traffic that's going to be generated, transmitted from end to end. So how much can we get through this pipe? It's a key indicator for the network performance. We can test it at line rate, bottleneck bandwidth, or committed information rate. I'll talk a little bit about that in just a second. Next is frame delay or latency, and that's basically the time it takes for the signal to get across the cables, through the switches, and back. So if we've got device to device, it can be measured in one direction, one-way delay, or RTD, round trip delay. So if we've got device going to another device, that would be one-way delay. We can measure one-way delay. Device to a loop back and coming back, we're going to measure round trip delay. And I'll talk a little bit about that and loop backs and stuff in just a second. Next one, jitter, frame delay variation or jitter. It's a variation in the response times of frames over the network. So as we're sending those frames, what is the variation in those? And you see, it's detrimental to frame loss, obviously, for real-time services. So next one, frame loss ratio. Basically, how many frames are we sending out versus how many frames are actually being delivered to that destination. Again, it's frame loss is detrimental to all network applications and services. So some of the keys there, some of the key causes on that could be signal levels, could be noise, could be, I talked earlier about crosstalk on the cables and that. So those are all kind of causes of frame loss. Next one is, so those are the KPIs, the primary KPIs, but there are a lot of other performance indicators that we can use. Committed burst size, that's how many bits can be sent per a certain time over to maintain the CIR, the committed information rate. So your CIR is what your service provider is saying, okay, we're going to give you 1 gig up and 1 gig down, let's say. So how many bits can we be sent a certain amount of time to maintain that? Also, maximum transmission unit. So that measures the maximum frame size allowed over that network. So if we've got, say, 3 switches and 2 of those switches are configured to support jumbo frames and one is set to 1518, then the 1518 is going to be your MTU. That one switch isn't set up properly, isn't configured properly. Control plane transparency, Dave's going to do an actual, we call it J-proof. Dave's going to do a quick demo on that in just a bit. And then bit error rate testing. We've talked about that a couple of times too. So those are kind of other key performance indicators that you can look at in addition to the ones to throughput, latency, frame delay. So how do we test these key performance indicators? It should include throughput, like we said, throughput, delay, frame loss, and jitter using various frame sizes. As I mentioned, you may have a network that works absolutely perfectly on small frame sizes, and other frame sizes just won't get through. So it's key to test it at different frame sizes. I'm going to run in just a minute an RFC 2544 test. You'll see we've got about 10 different frame sizes that you can turn on or turn off. And then if you wanted to customize it, put jumbo frames in there. You can customize it and put in enter jumbo frames. The key to that, the end result is going to be pass or fail assessment on the overall quality of that link. So by entering the information in that we want to achieve, that we should be getting, we can say, hey, we either met that criteria or didn't meet it, passed or failed. There are multiple methods that exist that address service level agreements. Viavi Quick Check, Dave mentioned that. It's something that can be run standalone, or it can be run as part of the RFC 2544 or the Y.1564. What that does is it checks your connectivity and makes sure that everything's set up properly before you go ahead and run an RFC. An RFC test could run for hours, days. We don't want to be running that test only to find out that the connectivity wasn't set up properly ahead of time. So it's a quick way, make sure everything's good to go before you run that test. And then Y.1564 is the last one. And Dave's going to get into each one of these in a little more detail and talk about which one is most applicable to your requirements. One thing we did mention is how we run some of these tests. There's head-to-head versus loopback testing. So head-to-head means we've got 2 pieces of equipment. We've got a T-Bird 5800 on one end, a T-Bird 5800 on the other end, and we're checking, we're running the tests one way out, and then the other unit's sending it back. The other way of doing it is with a loopback device. So we've got a 5800 on one end, and we've got a loopback device on the other end that's sending that information back. So testing with a loopback device offers some advantages. There's also advantages to testing head-to-head. Loopback device, a less experienced technician can set up the loopback device. Basically, put it in loopback mode, tell them, hey, Johnny, go and plug this in, and you can actually run the test. The seasoned technician is going to be sitting at the 5800 running the test. It'll give him a round trip delay measurement without any GPS. I'll talk about that in just a second. And then it's a single report containing bidirectional testing. And we'll show that again when we do the actual test. One of the keys there is a loopback device must invert the MAC address if traffic traverses a switch. So if you're sending it, just like in this picture here, this diagram here down below, we're sending the test packet. The destination address is our NSC. This is a Viavi NSC 100. We're sending that, it hits that, and now it sends it back. If that device doesn't invert it and tell it, hey, the destination address is a T-bird, it's going to still think that it's the NSC, and it's not going to be delivered. So one of the keys is the loopback device must invert the MAC address if traffic goes over a switch. Some of the benefits on the flip side to head-to-head, it allows you to isolate. So when we do a loopback device test, let's just say we're taking 4 milliseconds. We run the test, it takes 4 milliseconds. Well, we're assuming it's 2 up and 2 back. By doing a head-to-head test, now we can isolate the directions. We can isolate that, okay, it might have been 1 millisecond up and 3 milliseconds back. So we can isolate which leg has which delay versus just taking an average. So it allows for one-way delay versus a round-trip delay. On one-way delay testing, you're going to need a GPS, built-in GPS. And the reason for that is you need these 2 clocks to be synced, or else this will be on, what time is it now? 2:07, and the other one might be at 2:08, so you're not going to get accurate information. But if they're both synced to a GPS clock, we can you'll get accurate information, accurate measurements of both. With that, I'm going to pass it over to Dave, and he's going to finish up, and then we'll give you some examples of all these different tests we're about to talk about.
Okay, a variety of test applications for Ethernet are available on the equipment. We showed you some, focused on connectivity testing and component testing. But for service acceptance testing KPIs, there's a few main ways that Peter highlighted. The one to choose is kind of dependent on what you're doing. If you're doing service acceptance, you've just installed a network, you want to verify it's working properly, you have a choice between RFC 2544 and Y1564 on Viavi equipment anyway. RFC 2544 is the preferred method, for most users if it's a single stream workflow. So that means you don't have a VLAN, you don't have different classes of service. You just want to, you could have a VLAN, but you don't have different classes of service. You don't have multiple VLANs, and you just want to blast traffic out at the committed information rate and verify that all your KPIs are acceptable. RFC is a simple means of doing that. Viavi's enhanced the process for that over the years to be a very streamlined test. We'll highlight some of the things it does. But for single stream services, RFC is the way to go. If you do have different classes of service on 2 or more VLANs, then Y1564 offers significant advantages. You can use Y1564 for single stream services too. Works well, but it's a little bit more to configure if you want to do multiple frame sizes in addition to the classes of service. It's just a little bit more complex of a test. In either case, if the traffic is going over a service provider link, we had recommended an additional test called JProof to verify transparency. And if time permitting, I'm going to demonstrate that to you as well. And in either case, I guess as a pre-test, quick checks recommended, which we'll also demonstrate. RFC 2544, as I mentioned, measures throughput, frame loss, delay, and jitter. Can optionally do committed burst size too, so all your KPIs are covered. Generates a pass-fail report. It's Basically, you get a birth certificate for the circuit saying that it meets all the requirements that were promised in a service level agreement. Now, as written, the RFC 2544 was originally a lab test for switches and routers. So it was a very rigorous test for new equipment or to be accepted in a lab. It wasn't designed for Metro Ethernet service to be done on a LAN. So some of the durations were more optimized for lab use. Some of the way it was sequenced, again, was more optimized for lab use. Viavi recognized that early on, and we made a lot of improvements to it. We added the J-Quick check, a pre-sanity check that makes sure that you have connectivity before you invest maybe the 10, 20, 30 minutes. Yes, some people like to run 24 hours, but before that, we added a pre-check to catch a majority of the issues up front. We also changed the algorithm so we do throughput, latency, and jitter concurrently. If you followed RFC to the T, you would run each of those as individual tests. So we cut that test time down by a third. We added the burst test and some other improvements. So we have a very streamlined, very efficient RFC test. Again, that's preferred for most users for single stream services. Y1564 is a newer standard. It overcomes some of the drawbacks of RFC as it was written, mainly that it will it's a faster test. RFC spends a lot of time on latency as opposed to frame loss and throughput, which are more common issues to focus on. So it's a little bit more streamlined if you do a true RFC implementation, but I think Viavi addressed most of the issues that RFC addresses in its RFC implementation, at least for single stream services. But Y1564 will do a test on each service individually. It'll do a ramp test and verify that you can get a given information rate on each of the services. So you can test voice and data independently. And then it'll combine the two and do a multiple stream test to verify that the full committed information rate with all the streams traveling concurrently can get across that link. Now, these are the preferred method to use for service acceptance when you want a birth certificate, you want a report indicating that the test is passed. But test equipment also performs just a normal traffic generation mode where you can still measure these same KPIs, but you can see all your results in real time. So when you're troubleshooting, you don't want to wait 30 minutes to get your results. You want to know right away that if I change from this frame size to this frame size, or if I test at 300 meg versus 400 meg, or 100 gig versus 50 gig, is the test performance going to be different? So traffic generation mode allows you to do that. It allows you to send constant loads as opposed to bursty traffic or ramp traffic up. So you got a lot more flexibility in how you configure the unit, and you get more detailed results too. So I want to demonstrate all of these modes to you. Peter's going to start off with a demonstration of RFC 2544.
All right. Thanks, Dave. So what I've got running on my screen here is the RFC 2544 test. I can go in and configure all the different parameters. I've set this up ahead of time. This is an example of the quick check that we've talked about a couple of times. It's checking all of my connectivity, local port, auto negotiation, remote loop, everything's looped up. I've actually got that same AOC DAC cable hooked up to my 5800. I've got a dual port T-Bird 5800. So I've just got a 40 gig AOC DAC cable hooked up there. You'll see measured throughput here is 40 gig. So everything's set up, everything's ready to go. If I go back here and I load config, load files. So I've saved a configuration here and hit next, next. All right, so this is going to allow me to show you exactly what all the different settings and what's set up. So throughput test, I'm just going to do symmetric. So I'm keeping pretty much all of these, as Dave said, we've really streamlined the RFC 2544 test. I'm keeping all of these defaults pretty much set. Nothing to change here. If we did have encapsulation, we could go in here and enter the VLAN or VLAN within a VLAN, Q and Q. Just leave this again at the defaults. I've unchecked frame loss here. I'm going to do throughput, latency, and packet jitter. I can go in and here's where we're talking about the 10 different frame lengths. I can select any of these given frame lengths, but if there's one that I wanted to add, let's say a jumbo frame, I can go in here and add anything I want and type that in. So I've selected 64 and 1518 as my 2 frames. Everything's good here. I've set the test time to just 5 seconds, again, just for this, this quick demo purposes. And here we've got the different thresholds. So because I've set thresholds up here, we're going to be able to see, I'll show you what I'm talking about in just a minute. But here are my different thresholds. And now I can run that test. Next. So it's done the quick check. Everything tested out fine. It's passed. It's checking all the parameters that I've set up. And it's telling me I've got a 38 seconds. So depending on where you saw that I set for 5-second duration test time, that's going to impact this time remaining. So in this case, I've got 30 seconds remaining. If I've set thresholds, I will get a pass and fail result. If I didn't, I'll just get a blue check mark. So it'll run the test anyway, but there's nothing to compare it to. So I'm just going to get the test completed. In here, you'll see that I've got the test is actually running. So as Dave mentioned, one of the keys to Viavi's RFC testing is we're running throughput, latency, and packet jitter all at the same time, all being run concurrently. As that's running, I can go in here and click on a test. So it's done the 64, and now it's working on 1518 frame lengths. I can go back, I can click on packet jitter and look at the results on that one. And see, same thing, it's past 64. It's finishing up on 1518. It just finished and it passed. So now when I go back, I'm expecting to see all green check marks. Sure enough, everything's passed, all green check marks. Now we talked earlier about testing, test reports. If I click on this, there's a job manager that we use. It'll bring all of your customer name, your tech ID, all of this information over into your report. If I wanted to add any notes here, I could add some comments or some notes about the test, and then click on create report. It gives us 5 different types of reports that we can generate. I hit create report. I just selected PDF just to show you. I create report. It's going to generate the report. It's going to save the report in a PDF. And I had it checked off so that view the report after it's done. So here's my report. Here's the actual RFC test. You'll see the tests that I've done, throughput, latency, jitter, and then as I showed you earlier, it's going to show all of those individual tests. I have a tough time doing it with my mouse here, but it's going to show all of those individual tests and give you all the results on there. So that's the RFC kind of basic overview of an RFC 2544 test. It can be customized to meet your service level agreements and KPIs. And we'll pass it over to Dave. He's going to do a Y.1564 test for you.
Thank you. Let me switch back to my screen here. So I've already set up the Y1564 test. I'm kind of at the end of the setup, but I've set it up for a voice and a data stream on different VLANs. I set it up to generate traffic equivalent to 100 voice calls, and then the rest of the bandwidth I'm using for data. So I'm going to run both the tests in the suite. I've already done a quick check and looped up my far end device. So now I can go ahead and run the test. So as I mentioned, the 2 stages are service configuration and service performance. It's verifying the voice stream for initially, making sure that that traffic can get through. Hopefully I'll get a green check. After that, it should give me a green check for data. And then go through the service performance test. I got about a minute in total here. Now between RFC 2544 and RFC and Y1564, those again are your major tests for acceptance at layer 2. Now, there may be cases where you need to test at layer 3. If you're testing through routers, these tests need to include IP addressing. So for layer 3 testing, actually the exact same test suite can be performed. You can still do RFC 2544 and Y1564 tests. It's just that there's another screen that needs to be configured with IP addressing. Now, we also do recommend a layer 4 test. Again, it's a little bit outside of the scope of what we're covering today, but there's a separate RFC. It's called RFC 6349, and that test is supported on most Ethernet test sets, and it does a TCP throughput test. It's a little more thorough than something like a Ookla speed test that you may run for your home internet service. It actually it's a lot more thorough, and it gives you diagnostic information as well. So those things would complete out the test process. But again, for just strictly layer 2 testing, these are the big 2. This is finishing up here in about 20 seconds. At that point, I should have some more green check marks. And then if I wish to continue through the workflow, I would hit the next button. As Peter did, I could save a report and then archive that for future reference. So here we go. 3, 2, 1. And my test is passed. My frame loss was 0. My delay was negligible. And my delay variation or jitter was also negligible. So that is Y1564. I'm going to go ahead and exit out of that, and I'll show you just the regular layer 2 traffic test for troubleshooting. I'll do it on a copper interface. All our tests run pretty much the same, whether you're on copper or fiber, and whether you're testing at 1 gig or even 400 gig on our latest generation of Ethernet test sets. But give it just a moment for this to test up. I've already configured the other link for this because, as you know, you need a loopback device on the far end, and I'm testing T-Bird to T-Bird. So here we go. Oh, shoot. What did I do? I launched this on the wrong port. I apologize.
So Anthony, while he's setting that up, I can talk for a second on. So while Dave's getting that set up, I'm just going to talk quickly. One of the questions came in on what devices can we use for loopback devices. So this is a slide I just pulled up, Viavi loopback devices. Most current in legacy Viavi JDSU Ethernet test instruments can be automatically looped up and looped down by the T-Bird 5800. So we can use a JMEP. The NSC 100 is, let me grab my pointer here. NSC 100 is one of our newer products. You can use any one of the T-Bird 5800s. And ONA 1000 is another new device we've just come out with. MAP 2100 is a rack-mounted version of the T-Bird 5800, and then Fusion, which is a program. So the far-end test device set can be looped up remotely, and I'm not sure if that answers the question that came in. Can we talk about which dummy products that can make a loopback? So.
Yep. Yeah, that's our current test suite. Any of our older.
I'll transfer it back over to Dave. I think he's set up and he can talk about this a little bit more.
Okay, thank you, Peter. But any of our legacy equipment, if you have our older HST 3000s or test pads, yeah, they're viable loopback devices as well. Okay, I have a setup similar to that lower diagram of Peter's. I'm testing from a T-Bird into a layer 2 switch to another T-Bird. And this is the T-Bird that I'm going to generate traffic from. I've launched the test, so the next step would be to tap the setup button in order to configure a test. And there's a few different screens in setup that'll allow me to view the test I want to run. Now in Ethernet, we did get a question in earlier about whether you wanted to send out Ethernet test packets versus BERT patterns. We do give the ability to choose. That's in the data field here. So now I'm getting a little deep into the product, maybe for people that this is new to, but yeah, in reference to that question. This is where you can convert between just sending a BERT pattern. Now, when I do that, I'm just sending a PRBS, just ones and zeros. I'm not sending timestamps or sequence numbers that let me measure delay and frame loss, but I will get bit error rate. So that's one option there. Acterna then, that sends a sequence number and a timestamp so I can get bit error rate. If you want both, kind of to get the best of both worlds, at most of the rates that we test at, you can do an Acterna payload followed by BERT. And then you can get all of those KPIs. So that's what I'm going to set things to here. The traffic screen, I think I showed you a screenshot of that earlier, but that's where I could do a constant load, bursty traffic, or ramp traffic. And I'm going to send traffic out at line rate. In this case, my line rate is 1,000 meg a gig. I'm on a 1 gig interface. But those are the main things you need to set up to run a layer 2 traffic test. I can automatically loop up my far end device. It's telling me up here it looped up successfully, and I can start traffic. Once I start traffic, all my KPIs can be viewed. I'm sending a gig and receiving a gig. I have 21 microseconds of round trip delay, and we have resolution down into the nanoseconds. I have very little jitter. I'm just going through a single switch, and I'm the only device transmitting traffic, so there's not a whole lot of buffering going on. And this link looks good. I did take a few errors when I launched the test, and they were highlighted over here, but they're not accumulating. If I hit restart, that should clear up, and everything should run pretty clean. There's a lot of more detailed results you can get here than with an RFC as well. An interface, if it's optical, I can see signal levels. I can, can get frequency information. I could see graphs showing my throughput over time. For that matter, in real time, I can change my load. If I was taking errors at a full gig and I wanted to see, hey, if I drop it down to 900 meg, is this link going to run cleaner? Then I could see if my errors continue to accumulate. I could change my frame size in real time. So if it fails with short frames where I have the most frames per second, if I reduce the frames per second and send the same amount of information in half as many frames, is that going to affect my performance, or if it passes or not? So a lot of stuff I can do to characterize problems and troubleshoot them, kind of narrow down what exactly is causing problems when you have network performance issues. Now, lastly, one more thing I want to demonstrate you. I know we're running a little bit over on time here, but I do want to show you how the control plane testing works. Now, I'm testing through just a regular work group switch, so it's not a carrier Ethernet switch. It's not designed for network transparency. So it is going to fail, I'll tell you that ahead of time, but you can see how it fails, and watch out for this if you are evaluating carrier networks. So instead of sending regular traffic, I'm going to send what we refer to as J-proof traffic. That's our transparency test. Now I can set up what type of messages I want it to generate by just a spanning tree, but I'm going to do a quick config and add a few more messages. So it's going to send spanning tree, Cisco, and IEEE control plane messages. That's it for setting it up. Now I'm just going to go back to results. I'm going to loop up my far end device. It looped up, and then I'm going to start my frame sequence. I'm going to change my view here to show the JMEP results. And again, since this isn't a transparent link, hey, my spanning tree message isn't getting looped back to me. Again, this is a work group switch. It shouldn't be looping back. So, so that's expected. A few messages get through, but for the most part, this switch isn't going to, forward through all the control plane messages across those ports. Again, if this was a carrier Ethernet switch and I was connecting, my office in Melbourne to my office in Orlando, the link that if I'm getting layer 2 service from that service provider, that link should appear to be just a cable to me and should not be blocking these messages. So The provider is responsible for configuring the switch to be transparent, and if not, again, this test is going to fail. I think that concludes the demonstrations. I hope I answered the question regarding you doing bit error rate tests versus ATPs. Let me check for additional questions, or do you have any questions queued up, Peter, that you want to take a look at while I?
Yeah, I don't see any in the thing. There was a question on loopback devices. I think we answered that one.
Okay. Let me double check here, but in the meantime, I do want to thank everybody for their time and attention today.
Yeah, thank you, everyone. And let's give it a couple of minutes, see if any questions pop in there.
Yeah, I mean, we're available if anything, any demonstrations you'd like to see, anything. We'd be happy to do that now.
Right, we've got all the equipment set up here, so if there are, like Dave said, any questions. That's true. This is the last call on those acronyms. Please don't throw away sausage pizza. So, I don't know if Dave has any acronyms that he could throw out there.
No clean ones.
No, all right, all right. All people seem to need data processing. That's another one that I've heard. So, again, I think we, the open and interactive worked well. Dave and I weren't arguing or anything, or I didn't cut him off.
Okay, bye-bye. Thank you.
All right, thanks, everyone. We're going to wrap it up now, and thank you again for attending, and stay tuned. There's a lot of different YouTube live videos and different webinars and stuff coming up. Be sure to visit the Viavi site for all the updates and list of all future presentations. Thank you very much. Take care.